Today we'll be looking at types of functions. Our objectives will be to identify discrete and continuous functions, to identify constant functions, to identify linear functions, and to identify nonlinear functions. So let's start with discrete and continuous functions. I'll begin by giving you two pictures. What is it that you notice when you look at these two pictures? What pops out at you should be the fact that the one on the right has a continuous line that connects it, and the one on the left is made up of discrete pieces of data. Well, that is exactly what you have here. The first function is discrete, while the second one is continuous. Let me help give you a way you can remember this easily. A continuous function is one that you can draw without having to lift your pencil. There are no gaps or holes in it. That makes it continuous. The one on the left, obviously, you cannot do that with. That's discrete. Let's talk now about constant functions. I've given you here two constant functions. Let's examine first of all what makes them constant, and then we'll talk about the other difference. So let's look first at a constant function. In the one on the left, if I chose the x value of -3 and ask you what is the y that pairs with that, hopefully you would tell me it is 3. Well, if I chose a -1, you could tell me the y value is 3. If I picked a 1, you could tell me y is 3. And I hope you're beginning to notice, by the way, I did skip over it, but we could also have chosen 0 and you would have said 3. What you should be noticing here is that no matter which x I picked, you constantly told me that the value of y was 3. Well, let's notice on the other one what we have. When I choose x of -3, you still tell me 3. What about when I choose x is 0? The y is 3, but this time I also have the right to pick things in between, like a -2. Well, the y with that is still a 3. Or what if I picked 1/2? The y that pairs with that is 3. So what you have here is still a constant function. You're still telling me constantly y is the same thing. But what is the difference between these two functions then? Well, the one on the left is a discrete constant function, and the one on the right is a continuous constant function. Note that constant functions have the same y value all the time. But once again, the definitions of discrete and continuous are the same. The one on the right I can draw without picking up my pencil. Therefore, it is continuous. Let's now look at linear functions. Remember when we talked about linear equations and we said that a linear equation could be written in the form y is equal to mx plus b. Well, now we're looking at linear functions. A function is linear if it can be written by f of x is equal to mx plus b. Let's take some examples, and what I'd like for you to do is grab your calculator and graph these functions just so that you can see they really are straight lines. By the way, let's identify the slope and the y-intercept here. The slope in this one is 6. The y-intercept is -4. And let me remind you that that is a point, 0, -4. In the next one, we have g of x is equal to 9x. What is our slope? Well, it is a 9. It's the number that's attached to that x. What is your y-intercept? Well, we don't see one written here, but let me make sure you understand. Right there it is. And so our y-intercept this time would be the origin, or 0, 0. This next one we have is h of r is equal to 7 minus 9r. It is written in a little different order, but let me remind you, the slope is still a -9. And the y-intercept this time is a +7, which would be written like that. And then the last one you have is f of x is equal to 9. Well, this time, what is your slope? Well, we don't see any number in front of an x. We don't even see an x. So your slope this time is equal to 0 because 0x is what's there. You don't see it written. If you think of it, it would have looked like this, and that's why you don't see it. So your slope is 0, and what is your y-intercept? 0, 9. By the way, that last one is nothing more than a horizontal line located 9 positions up the y-axis. Now what we want to do is identify some nonlinear functions. This seems a little easier to me. when we look at this, if I ask you if that's linear, the question you need to ask yourself is it a straight line? Well, the obvious answer is no, it's not. By the way, this function was f of x is equal to 3x squared minus 4. Let's look at another one. Is it linear? The answer is obviously not. And this one happens to be f of x is equal to 3x cubed minus 4. You should be getting a feeling now that things that have x squareds and things that have x cubed are not going to be linear functions. And let's look at this last one. This one turns out to be f of x is equal to the square root of x, which is also nonlinear. Now we want to move to recognizing linear and nonlinear data when they're written in the form of a chart. So let's look at that. Here I have a table, and across the top I have my domain elements, and along the bottom I have my range elements, or my y's. One way you could determine if this is linear would be to examine the slope between each of these pairs of points. For instance, I could calculate the slope of these 2 points, then I could calculate the slope of these 2 points, and then I could calculate the slope of these 2 points, and then I could calculate the slope of these 2 points. Well, that would take a little while to do, so let's see if there's an easier way. And the answer is yes, there is. First of all, let's say that I look at the increase here. Well, it's 1 unit, and the increase here is 60. Let's go back to the top again. 1 unit, what do you see here? 60. 1 unit, 60, 1 unit, and 60. Let me ask you then, is this data linear? And the answer is yes, it is. For every time that x increases by 1, the y value increases by 60. That data would indeed be linear if you were to draw the graph. Let's look at our next table. This time I want you to notice we're going to be jumping from -3 to 0, so that's an increase of how many units? 3. So for the 3 on the top, let me just write that up there so we'll remember. For 3 on the top, we have a 2-unit increase on the bottom. We have 3 more on the top, so we're looking for 2 on the bottom if it's linear. Well, the minute I see this as a 3, I can tell you without going any further that this data is nonlinear. Let's move on. Another table. This time, I'm jumping by a unit of 5 on the top. But how much on the bottom? It gets 2 bigger. An increase of 5, this gets 2 bigger. An increase of 5, an increase of 2, an increase of 5, and an increase of 2. What could you then tell me about the data in this chart? It is indeed linear. Let's look at one more. I want you to notice this time I have an increase on the top of 2 and an increase on the bottom of what? -6. 2, let me just write that up there so you see it. -6. How much is your increase here? Now be careful, don't bail out too soon. An increase of 4 on the top means I should have an increase of what in the denominator? A -12. This increase is twice as big on the top, so I need the decrease in the bottom to be twice as big. And it is. So let's continue then to see. This time I jump 1 position on the top. I would expect it to be 3 positions on the bottom. It turns out that that data is linear, even though it doesn't look like it to begin with. If that one bothers you a little bit, let me ask you to go back to the concept of calculating slopes. Calculate the slope of those 2 numbers. Calculate the slope of these, and you'll see that you end up with the same slope every time. And you can do all the other pairs if you want to. So now I would assume that you can actually recognize linear and nonlinear data even without drawing the graph by simply doing some calculations. And that may be a really good assumption, but I want to leave you with this saying from Confucius. I hear and I forget. I see and I remember. I do, and I understand. I encourage you to do some doing. See you next time. Bye-bye.